this unit, we're going to talk about basic probability theory. The problems we're going to be looking at are often referred to as counting problems. To get started, we have to define some terms and learn some new notation. Particularly, we're going to define the sample space. We're going to define what an event is. We're going to define what the complement of an event is. And we're going to explain that notation, the P with the parentheses. So let's start with the sample space. The sample space is the set of all possible outcomes of your experiment, whatever that experiment is. So if you're flipping a coin, the sample space would be the set of heads and tails. Now, if you're rolling your standard Monopoly die, the sample space would be the set of numbers 1, 2, 3, 4, 5, and 6. Now notice I didn't say 1 through 6. 1 through 6 would be continuous and would include everything in between the 1 and the 6, but this is definitely a discrete random variable. An event is any collection of outcomes from the sample space. Okay, this is also known as a subset of the sample space if you're familiar with set theory. And if you are familiar with set theory, an event does not have to be a proper subset. Okay, so let's look at a few examples. And again, we'll use the rolling one fair die example because that's something we're all familiar with. And I've defined the event A to be all the odd numbered outcomes. So that would include the 1, the 3, and the 5. B, I'm going to define as the set of 1, 2, 3, and 5. Again, those are 4 outcomes from the larger sample space of 1, 2, 3, 4, 5, 6. Now, an event does not have to be more than one outcome. So rolling a 6 by itself, okay, even though that's only one possible outcome from the sample space, that is still an event. Next, I want to define the complement of an event. A complement of an event is the set of all outcomes that are part of the sample space, but were not part of the original event. Okay, so the complement of an event is everything it takes to be added to your event to give you the entire sample space. Now, one more time, we're going to talk about the die. So we defined the event A a minute ago as being an odd number. So the complement of that, in here I'm going to use the A with the superscript C for the complement of event A, would be that we roll an even number. Right? Because the odds and the evens together, if we union those, to use set notation, okay, if we take the union of an event and its complement, they make up the entire sample space. Now, event B had the numbers 1, 2, 3, and 5. So in our sample space, we're missing the 4 and 6. So our complement of B would just be the event that we roll a 4 or a 6. And finally, the complement of event C would be all the numbers 1, 2, 3, 4, and 5, because when you pair them up with the 6, we get the entire sample space. Now, I want to point out that the book uses a little bit different notation than I am here. It uses this A bar for the complement of A or B bar for the complement of B. Now, I don't really like that in the statistics course because that could be confused with the sample mean. Right? X bar is just the mean of the variable X. Context should dictate which is which. Now, regardless of whether or not we use the bar notation or the superscript C notation for the complement, okay, it's not going to change what happens in our class at all because we're actually going to just write out the complement. If I want the complement of odd, I will write even. I will not write A superscript C or A bar. So whenever we write P parentheses in probability, okay, this represents a probability of whatever we have written inside that blank space. It's the probability of that thing happening. Right? So if we put a 3 inside those parentheses, and we're talking about the dice that we've been rolling here for the last several examples, that would be the probability of rolling a 3. Okay? Now, if we write inside the parentheses, Peyton Manning shows up to your next class. That would be the probability that Peyton Manning shows up to your next class. Now let's talk about some basic rules of probability theory. Okay. So first of all, probability is always between 0 and 1. Okay. A probability of 0 means the event cannot happen, and a probability of 1 means the event will happen. Okay. Now, If you take a probability and multiply it by 100, you have the percent chance of that event happening. So if something has a probability of 0, it has a 0% chance of happening. If something has a probability of 1, it has a 100% chance of happening. If you take the probability of an event happening plus the probability of its complement happening, they're going to add up to 1. Okay? Because every event either does or does not happen. So A is my event. A complement is everything that's not A. And either A will or A will not happen. So when you take those two probabilities, they have to add up to 1. Now, if you think about that, you already knew this rule, right? If I asked you, what's the chance it rains tomorrow, given there's a 20% chance it doesn't rain, you would all tell me that there's an 80% chance of rain because you know 20% plus 80% is 100% and it either will or will not rain. If we do a little bit of algebra, we come up with this version of the formula, which simply says the probability of some event A happening is 1 minus the probability of its complement. So the probability that something does happen is 1 minus the probability that it does not happen. Or if we flip our perspective, if you take and subtract the probability of it happening from 1, you get the probability that it does not happen. Now again, those three equations on the screen are all the same equation with just a tiny bit of algebra. So if we're in a situation like we have been, where all of our outcomes are equally likely, that is, when we roll our fair die, the 1, 2, 3, 4, 5, and 6 all have an equal chance of being the outcome that we get. Okay? In this case, the probability of some event A is equal to the total number of outcomes where event A happens, divided by the total number of outcomes in the sample space. And again, this is where we get the terminology I used earlier about counting problems. If we can just say there's this many to choose from, and here's how many of those give me what I'm looking for, we have our probability. When every item in our population or sample space is equally likely to be the one we end up with. Okay, so what we're really doing here is simply finding what proportion of the population or sample space does the event occupy. Right? And so if we multiply proportions by 100, we get percentages again. Right? So if something occupies 40% of the population, then it has a 0.4 probability of happening. So when we actually go to figure out our fractions, I want you to ask yourself two questions here. Okay? And I want you to do it in this order. So first, ask yourself, how many are you actually choosing from right now? So at this moment, when I'm doing my experiment, I may be in the context of a much bigger problem, but for each fraction we're going to determine, we're looking at this very moment, how many are you actually choosing from? That's going to be your denominator. Always start with your denominator. You're going to be tempted to try and get the numerator figured out first. Don't. Start with the denominator. How many are you actually choosing from at this moment? And then, out of those, how many of them are what you're looking for? So let's look at a few examples. Again, from the fair die, because we all understand what's happening with the fair die. So, I want the probability of rolling an odd number. Well, again, when we roll the fair die, there are 6 numbers to choose from. That's my denominator. And out of those 6, how many are what I'm looking for? Odd. Well, 3 of the 6, of course. And that means we end up with 3/6, which is also equal to 1/2. Now, if I want the probability of getting our second event, event B, 1, 2, 3, or 5. Again, we roll the die, all 6 numbers are equally likely. We have to start by establishing that they're equally likely. And then we can ask ourselves our 2 questions. There are 6 to choose from. How many of those 6 belong to this event? 4. So the probability of getting a 1, 2, 3, or 5 is equal to 4/6, or 2/3. And the probability of getting a 6 would be 1 out of 6. But again, I always start with my denominator. Here we have what is known as a two-way or contingency table. Now down the left-hand side, you see what kind of cell phone each person in our survey has. Some people owned an iPhone, And at the far right, you see the total number of people who owned an iPhone, 1,764. We have the number of people in our survey who owned an Android phone and the number of people who did not own a smartphone at all. And again, each row represents each type of phone. And at the far right, we have our totals. Now our columns represent the age group of each person in our survey. So there were, in the first column, 1,088 people who were in the 10 to 25 age group. And then we work our way across. So in the very, very bottom right-hand corner, that is our grand total. That is our sample size. That is our population size in this case, because we're going to take from this data, this information is going to be the population or sample space that we are going to sample from in the next several examples. Okay. So if you add up the totals in the right-hand column, you get 4,536. If you add up all the age group totals at the bottom row, you get 4,536. Now, let's look at some examples. If we randomly select one person out of these 4,536, again, in our survey, we have all these results, and now we're going to randomly pick one of the survey results or one of the people that was surveyed. So all 4,536 people are equally likely to be the one person we randomly select. I'm not saying that the probability of them being in each age group, that the age groups are equally likely. I'm not saying that their cell phone status is equally likely. Simply that out of this group of 4,536 people, when we randomly pick one out, there's an equally likely chance that we come back with each of those individuals. So the first problem we want to look at is the probability that they own an iPhone. So there are 4,536 to choose from. 1,764 of those own an iPhone. So again, we start with our denominator. How many are there to choose from? Then we get our numerator. How many of those that we're choosing from give me what I want? The probability that someone is over 55. Still 4,536 because we're choosing one from the entire group. So there's 4,536 to choose from. Out of those, 766 are in the age group we're looking for. So our probability is simply 766 out of 4,536. Finally, I want to find the probability they do not own a smartphone. Once again, 4,536 to choose from, 756 who do not own a smartphone. There's our fraction waiting for us to put it together. Now I want to talk about what is known as conditional probability. Okay, so we need some terminology and notation here. So over here on the left-hand side, you see the P parentheses, and inside the parentheses, you have this A and then a vertical line B. Okay, so that is literally read the probability that A happens given or knowing that B happens. Okay, so we're no longer looking for the probability of an event happening in a vacuum. We're looking for the probability that the event A happens under the circumstances, knowing or given or when B happens. Okay, so that's why this is referred to as conditional probability. Okay, so again, that vertical line is not a divising, it's not A divided by B. Okay, that vertical line literally is read as the word given. So we're going to stick to our rolling a fair six-sided die. So here I want the probability that our result is a 3 given or knowing that it is odd. So we know the result of the die is odd. We don't know what it's going to be, but we know it was an odd number. So at this moment, knowing that the result was odd, or given that it was odd, there are actually only 3 numbers to choose from. We know that it's either a 1, a 3, or a 5. So in terms of our fraction, how many are there to choose from at this moment? The answer is 3. Now, out of those 3 numbers, 1, 3, and 5, how many of them are the 3 we're looking for? Well, there's only 1 3. So the probability that we get a 3, given or under the condition that the result is odd, is equal to 1/3. Now, notice this is very different than the probability of getting a 3, which would be 1/6. Right? Because we have the added information. We don't know what the outcome is, but we do know it's odd, or at least we're only interested in the chances of getting the 3 when we get an odd number. Now, in example B here, I'm going to reverse the order. Now I'm interested in the probability that it's an odd number given the fact that it is 3. Well, given we got a 3, that means there's only one number to choose from. The result is a 3. Makes our life pretty easy. How many are there to choose from right now? 1, because we know we got a 3. How many of those are odd? 1, because the 3 is odd. So the probability of getting an odd number, given that we know the result is a 3, is going to be equal to 1. Remember that the probability being 1 means that the event must happen. Okay, so we would also accept the fact that simply knowing that we have a 3, we must have an odd number means the probability that the number is odd, given it was a 3, was equal to 1. Now, I want to look at some more conditional probability problems back with our two-way table here. We're still selecting one person from the group. And the first thing I want to find is the probability that the one person we select owns an Android phone given or under the condition that they are in the 10 to 25 age group. Okay, so we know, even though there were 4,536 people to choose from, we've got the sneak peek. We're only interested in the cases where they finally ended up in this 10 to 25 age group. So, we look at the 10 to 25 column. There are 1,088 people to choose from. So that's our denominator. Remember, the two questions we ask ourselves. At this moment, how many are there to choose from? Well, given they're in the age group 10 to 25, there are only 1,088 to choose from right now. Out of those, how many are going to give us what we want? Owning an Android. Well, in this age group, right? And again, we know we're in this age group, so we're limiting ourselves to this 10 to 25 age group. And then there are 425 to choose from. So our probability simply becomes 425 over 1,088. Now, let's look at another example. All I've done here is reverse the order from the Android and the 10 to 25 age group, but it is going to completely change our analysis. So we want the probability they're in this age group given they own an Android phone. So now we know they're in this second row where we have the Android phones. So at this moment, how many are there to choose from? Knowing they own an Android phone, there are 2,016 to choose from. Now, second question, out of those 2,016 we're choosing from, how many give us what we want? Someone in the 10 to 25 age group. And that's 425. So the probability that they are in the 10 to 25 age group, given they own an Android phone, is going to be 425 out of 2016. Okay, so you see how different these two probabilities are. Changing the order absolutely changed a lot of things. Now, part C here, we've written this with the notation. Remember that vertical line is read given. Okay, so this is the probability that they do not own a smartphone given they are over 55. So I want you to pause the video and practice. This is your chance to see if you're figuring things out. So go ahead and pause the video now and do this problem. So we know they're over 55. We're given they're over 55, so we're here in the column of over 55. There are 766 to choose from, and out of those, 244 do not own a smartphone. So the probability they do not own a smartphone, given they're over 55, is 244 over 766. So hopefully that's what you got. Now, I want to look a little bit more closely at the conditional probability. We've seen this before. Again, this is just reminding you of what the notation is. But this time I'm going to roll 2 fair 6-sided dice. And I want to find the probability that the second is a 6, given the fact that the first is a 6. So we have 2 dice. Okay. Now, we know the first one was a 6. Does that affect the probability of the second one being a 6? Does what happens on the first die in any way change the probability of the second die? And the answer is no. So the probability that the second die is a 6 given the first is a 6 is just 1/6. Because that is the probability that the second die would be a 6, period. Right? The fact that there's 2 dice here doesn't change anything for us. Okay. Now, similarly, if I said, what's the probability that the second die is odd given the first is odd? Well, once again, whether or not the first die turns out to be odd in no way changes the probabilities of the second die. Okay. So the probability that the second die is odd would just be 1/2. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!